Hello, welcome to the first video in our fourth unit of our grade 11 University College math class. This unit is trigonometry, and this first lesson is the Pythagorean Theorem and the primary trig ratios. So what's nice about this unit and this lesson is that for most of you, this is going to be entirely review. For those coming from grade 10 applied, you will have a couple of new lessons towards the end of the unit, but otherwise it's pretty straightforward. So let's start with some triangle properties. I've already got them filled in. Obviously, one of the things we know about a triangle is it has three sides and three angles, three interior angles. The sum of those three interior angles is 180 degrees. And when we talk about having a right angle in a triangle, what that means is one angle that measures 90 degrees. In this triangle that we have down in example number 1, you'll notice that the way that we label a triangle is capital letters take the vertices, which are like the corners, and the side across from that uppercase letter gets the lowercase same letter. So what I'm talking about here is if I call this angle A, then the side all the way across the triangle from it is little a. And if I label this C, the side across from it is little c. And if I label this B, the side across from it is little b. The last piece of information to get under control for us is just that the longest side of a right angle triangle is called the hypotenuse, and the hypotenuse is always across from the 90-degree angle. That's our setup. So why do we want to learn about triangles? Well, there's a lot of triangles out in the world, and triangles have unique properties. Obviously, the goal of this unit is to develop some tools that will help us, given triangles, either right angle triangles or non-right angle triangles, give us tools to help find missing angles and missing sides. And again, the applications for this are all over the place in the real world. So let's start with one that you are already very familiar with, which is the Pythagorean Theorem. Now, the Pythagorean Theorem, I've listed it here as two versions, but essentially this one right here, this is like the actual Pythagorean Theorem. And the actual Pythagorean Theorem is explained as the sum of the square of the largest side, so the side that is the hypotenuse, the square of that side is equal to the sum of the squares of the other two sides. Which means if you can imagine, and I'll just try to do it off of maybe this triangle here, what that is essentially saying is imagine that you've got a square being drawn off this thing, and its area will be equal to the sum of the areas drawn off of the other two sides. Now those are obviously not perfect squares, but the idea is that if you were to add the amount of area in here and in here, it would total the area in here. That's where you get this whole squaring idea from. So how do we use the Pythagorean Theorem? Well, it just really depends on what side of a triangle you've been given. So if we look at our first example, what we have here is triangle ABC, and we are being asked to find side little a, I guess. I see I've got little b's in here, so maybe we'll fix that. We've been given the hypotenuse in this right angle triangle, 4.8 centimeters, and we've been given side little b, which is 3.6 centimeters. So for us, maybe we'll swap this up a little bit just to make it a little more consistent. Make these a's. So we have, if we're using our Pythagorean theorem, we substitute 4.8 in for our hypotenuse, 3.6 in for one of our sides, and side little a is the one that we're looking for. Now in order to isolate side little a, we need to bring 3.6 squared to the other side of the equation. So we're going to transpose that over to the other side by subtracting 3.6 squared from both sides of the equation. Now I've rewritten this with the variable that we're looking for, a squared on the left, but it's the same thing. A squared equals 4.8 squared minus 3.6 squared, and as we work our way through it, 4.8 squared minus 3.6 squared equals 10 even. And the way that we get a is to take the square root of 10, which gives us 3.17, and I think the units were centimeters. So that's how you use the Pythagorean theorem to find a missing side length that's not the hypotenuse. In this question over here, we've been given let's have a look at the triangle first before we jump into it. So here's our right angle. The side across from it is our hypotenuse. It happens to be the side that we're looking for. So if we're going to build this thing following the lettering system that we worked on, this is little w and this is little v. And if we're going to write out the Pythagorean theorem using the letters in this particular triangle, we have u squared, which is our hypotenuse, is equal to the sum, which is the addition part, of the other two sides squared. And now we're just going to do some substitution. So v squared is going to be equal to 30 squared plus 16 squared. Let's get our handy calculator rocking on this. Now again, I don't need an intermediate step where you figure each of them out. You can just type this thing in. So we've got 30 squared plus 16 squared. It's going to give us 1,156. And how do we isolate little u? We take the square root of both sides, which gives us u is equal to 34. And I don't think there was any unit of measure there, so just 34 units to figure this one out. Let's have a look at the last one. So in the last one, again, let's do a little bit of labeling. So if we're doing some labeling here, if we've got side, or rather angle D, this side here is little d. If we have angle B, this side is little b, that's already done for us. And if this is angle C, then this side over here is little c. So again, the side that we're looking for this time happens to be the hypotenuse. So let's rewrite this using the letters from the triangle we've been provided. So b squared, which is our hypotenuse squared, is equal to the sum of the other two sides squared. So let's do some substitution. We'll put in 93.0 squared plus 27.5 squared. And again, I don't need to see an intermediate step here. You can just jump right to both the squaring and the addition. So that's going to be 93.0 squared plus 27.5 squared, and that's going to give us 9,405.25. So again, I don't want you to do any rounding here at this step. You might be like, oh, should I round this? You absolutely should not round if you can help it until the final step. And we're just about at the final step. We isolate b by taking the square root of both sides, and the square root of both sides gives us 97.0 millimeters approximately. Again, that was 96.98, so that would round up to 97.0. I don't remember if it said it. Oh, it did say it in the question. It says round our answers to one decimal place. If there's no instruction given as to how you should round this, our general rule of thumb for side lengths in a right angle triangle, or I guess any of the trig unit, is one decimal place by default. So this is how you do the Pythagorean theorem. Hopefully that makes sense to you. We're at about the 8-minute mark now, so I'm going to push onwards and we're going to do the primary trig ratios for the right angle triangle, just talk about that, and then maybe we'll do a part 2 where we work on example 3 and 4. So Pythagorean theorem, one of the tools we have here when we're working with right angle triangles. Sum of interior angles, where we know the sum of the 3 interior angles of a right angle triangle, or any triangle, are 180 degrees. The last tool we're going to develop in our tool belt is primary trig ratios for right angle triangles. The thing to remember here is that from a given reference angle, so the reference angle here we're using is angle A, because it has our little theta here. And theta is just sort of a fancy Greek letter that we use for often. We use it for unknown angles. So from this particular reference angle, we're going to label all 3 sides of our triangle, not as their letters, but as their relationship to the reference angle. So the hypotenuse is always going to be the hypotenuse. It's across from the 90-degree angle. That one makes a ton of sense. That one's pretty familiar for everybody. The next side that I'd like to label is the one across from our reference angle, and that is our opposite side. That leaves us with the adjacent side last. Adjacent means beside, so it is beside our reference angle, but not the hypotenuse. So that's how you go about labeling the opposite, adjacent, and hypotenuse sides from a reference angle. That's the order I normally do it in anyway, is I identify the hypotenuse first across from the 90, identify the opposite side across from my reference angle, and the remaining side is the adjacent. And of course that also makes sense in that it is beside our reference angle. So that's how we go about labeling it. The next piece is just a little something to remember, which is there are particular configurations of ratios of sides that we've given names to. And these names, people always ask, like, what do they mean? They don't mean anything. They're just the names that people have assigned to them. So the sine reference, or the sine ratio from our reference angle takes the opposite side and divides it by the hypotenuse. So that's sine. The cosine ratio from our reference angle is the adjacent side divided by our hypotenuse. And last but not least, the tangent ratio from our reference angle is equal to the opposite side divided by the adjacent side. So I do want to point out that these are all, maybe I'll write that down over here, these are all 3 variable equations. And that's important for us because as we move forward and use primary trig ratios to find pieces of information, we're going to only need 2 in order to find the third. So of course the 3 variables I'm talking about are the reference angle and the 2 side lengths. Reference angle, 2 side lengths, reference angle, and 2 side lengths. So those are the variables that we might be able to work with. The mnemonic device that people use to memorize this is SOHCAHTOA. You don't really have to use it if you don't want to. I don't really use it. I just try to remember that the sine ratio from a reference angle is opposite over hypotenuse. Cosine from a reference angle is adjacent over hypotenuse. Tangent from a ratio, or tangent from a reference angle is opposite over adjacent. So there's our setup. We're going to go through and work the problems in our next video.